Okay, so today we're going to lay the wire flat on our desk. Let's have, Isaac Patrick, let's have the current moving towards the front of the room. You can't use the right-hand rule until you know which way the current's going. Oh my gosh, you got better.
Yeah, my bus was late.
Great. All you really missed was going over the test.
Okay.
So today's not a great day during lunch, but Friday, if you want, we could spend. I could let you sit down with yours and mine. All right. So the current's moving towards the front of the room. I want to know what's the direction of the magnetic field on the right side of the wire, directly on the right side of the wire. So see if you remember how to use the right-hand rule to be able to answer that question. What is the direction of the magnetic field due to the wire directly on your right-hand side of the wire? Hi. What?
Oh, I was.
So
I was just scratching.
I'm going to make sure that my thumb points towards the front of the room and then wrap my hands around the wire. And my fingers on the right side of the wire are pointing down towards the floor. Right? So the magnetic field directly on the right side of your wire should point down towards the floor. Boom. Alright, so that's what we did last time. Now let's talk about some other configurations of wires. So now I don't want to have a straight wire anymore. I want to have a loop of wire. So go ahead and clip the two alligator clips together. I'm going to do it on the board, but I want to do a bigger wire on the board, so I'm going to get another section and get some magnets to help me put it up. And what I'd like to do for our loops is to test use the right-hand rule to test the direction of the magnetic field at a few different places. Specifically, a few different places on the inside of the loop. So while you're waiting for me to set up, why don't you go ahead and do it? Just pick lay your coil down, your loop down, and just test the magnetic field at a few different places on the inside of your loop. Oh, which way do we want to make current go? Clockwise or counterclockwise?
Clockwise.
I heard one vote for each. Let's do counterclockwise. What does IB call that though? What do they call that in English? Anti-clockwise, right? So anti-clockwise is the direction of our current. Let's test the direction of the magnetic field right here, and right here, and right here. Right? So yours is laying down on your desk, right? Fine. I have mine up on the board, whatever. We would treat it in a similar way. So up here, right, I make sure that my thumb points to the left, and then underneath the wire, below the wire, on the inside of the loop, my fingers are pointing out, back. Yours should be pointing what? Up towards the ceiling? Right? Okay. Now, in physics world, if something points out of the plane of the paper or out of the board, we actually do represent it with a dot. If it points into the board or into the paper, we represent it with an X. So I'm just going to, even though I drew a dot to be the spot where I wanted to test the field, I'm just going to leave that dot. I'm just going to leave it there. And that means that the field points out of the plane of the board. All right, I'm going to do it here also. I'm going to move my magnet so I can actually get my hand there. So my thumb still points in the direction of the current, which would be anti-clockwise. And then on the inside of the loop, my fingers again point out of the plane of the board. Yours should again point up towards the ceiling. And I'll do it again at this last spot, making sure that my thumb points in the anti-clockwise direction. And yet again on the inside of the loop, the magnetic field points out of the board. Yours should point towards the ceiling. So guess, all right, so questions about testing it in those three places and getting the same result before we talk about like the ramifications of that result. All right. Well, what are the ramifications of that result? I only have Liam. I'm getting bored here, Liam and Patrick and Jacob. Amanda. So anywhere that we test it inside the loop, yes, the magnetic field due to the wire should point out. And there's one other little step I want to take with that. Jake.
It's outside of 1.8.
That is true, but I actually don't care about it. Liam.
It's in the same position or same orientation of the wire pointing in the same direction.
So what I do, I think the biggest outcome of that is that the field is strong inside this loop. It's strong because at every position, we have the magnetic field from this piece of wire, and this piece of wire, and this piece of wire, and this piece of wire, right? They're all pointing in the exact same direction. So everywhere inside this loop, the field is adding and adding and adding and adding, and it can be quite strong, very strong. Since that wasn't obvious, let's test that. Let's make sure that we can see and agree that that's true. So let's actually move over by Brian's. Wait, who went? Oh, Christina left. Let's go and meet by Brian's desk. You don't really need to bring anything. I just want to bring a few wires. We'll use Brian's compass. Patrick, can you just grab the camera, bring it closer, point it down at the desk. In fact, can you do that? You can just move this arm so that we can see the desk. We actually maybe should bring it closer so we can see the compass would be the important thing. Yeah, that's better. All right. So I don't want the loop yet. First, I just want to remind us what the compass deflection looked like when we had a straight wire. And we did do that last class, right?
Yeah.
Okay. And it got deflected like a lot or a little or what?
Not that much.
It was like some, right? Now actually, we better make sure we know what direction the magnetic field should be at the location of the compass due to the wire, right? Because if it's in the same direction as the Earth's, we're probably, obviously not going to see a deflection. You guys come closer. There's no way you can see the way that the compass points. So right now it's pointing that way because of the Earth. I want to use the right-hand rule to determine the direction of the magnetic field there due to the wire. So the current goes from positive over to negative, so my thumb needs to point that way, right? I wrap my fingers around the wire, and underneath the wire, the magnetic field is pointing that way. So that's great. That's about perpendicular to the Earth's magnetic field, so hopefully we'll see a deflection. So all I need to do is change the resistance of this from 100,000 5 ohms to just 5 ohms, and hopefully we'll see it. And we saw it, right? Deflected by about 20 degrees. So I want to redo that, but this time I want to put the compass inside a loop of wire. Thank you. Great, thanks. And again, I do feel that we need to retest the direction of the magnetic field that we should see inside this loop. I'm just going to put this one here to hold the loop together. All right, so the loop is, which way is the darn current going? It goes here, here, and then I'm masking which way, all right, so it goes this way. So my thumb would point there, and on the inside of the loop, it points down. That's problematic. Let me stand this loop up. Let me stand this loop up, and we'll put the compass inside, and then we'll do, I don't want it to point down, because that's just going to force the little needle into the table, and we won't see anything. So let me do it again. The current's going it's going this way around the loop. So my thumb would point that way. It should point exactly towards the camera, I think. Can somebody confirm that? All right, so this time, I think we're going to see a way more severe deflection, mostly because the strength of, no, let's point it the same way that it should have gone before. Before it was that, yeah, so let's actually point it, so because I'm hoping that we see a stronger deflection than we just saw before. All right, let's try. Oh my gosh, yeah, except it went the wrong way. So I must have done the right-hand rule wrong. The current is leaving here, it's going that way, this way, and then it's going around this way. So my thumb, my thumb points that way, and inside, my fingers are pointing that way. I must have somehow did it wrong. But I saw a more severe deflection, which is really all that I wanted to see. So let's quit while we're ahead and say, yeah, absolutely, inside this coil, we have a stronger magnetic field due to more chunks of wire. Shankar, I hope you appreciate this. There's one other thing that we could do to make, well, there's a few things we could do to make the field inside our coil even stronger than it is now, right? What are some of those things? Now I got lots of hands. Matt.
Keep wrapping it like a couple more
More
times.
coils. I can keep wrapping. In fact, I had about 1.5 coils there. We could absolutely do more coils. There is another thing I think is worth mentioning. Brian.
Would it be the tighter it is, the stronger it is?
Yes, but I made it as tight as I could there. Kevin.
I think you put like a piece of iron or something.
Yeah, you did the reading. Good job. We could use more current, right? We could use more current. But if we have more coils, right, we kind of have a name for that. We call that device a solenoid. So here we're showing how many coils. Well, this is like a half a coil. So half, 1.5, 2.5, 3.5, and another half. So we have about 4 coils here. If we made them closer together, then yes, we should absolutely have a stronger magnetic field, because the magnetic field, again, due to each coil, should be adding to each other. So we call that a solenoid, and probably not today, but maybe next time or after our midterm, we'll play with solenoid a little bit. That's what this thing over next to Sarah is. Right? She's got a whole bunch of loops of wire. All right, so yeah, we'll come back to that at a future date. I don't really want to review the first right-hand rule. So our other objective for today is discussing the direction of the force that acts on a moving charge. All right, so a moving charge creates a magnetic field, its own magnetic field. If it's moving through somebody else's magnetic field, those two magnetic fields might be influenced by each other, right? Magnets push and pull on other magnets sometimes. So if our charge is acting like a magnet and it's moving through a magnetic field, it's going to get forced. And our only other objective that I want to address today is establishing the direction of that force. But before we get there, let's just talk about our 2 criteria that have to be met in order for a charge to get forced by a magnetic field. There's only 2 criteria. One of them is that the charge has to be moving. If it's not moving, it's not acting like a magnet itself, so it's not going to get pushed or pulled on by other magnets. So I could have a solitary proton, right? I could put it right next to these really strong magnets, and it's not going to feel anything from them, unless it's moving. All right, so the charge has to have a velocity, and some of that velocity has to be perpendicular to the magnetic field. It doesn't have to be totally perpendicular, but it has to be at least partially perpendicular. Now, there are equations that we'll get to later for this. I was slightly disappointed to learn that nowhere at Biotech do we learn about the cross product, which is like a calculus thing. But all of this stuff about perpendicular and right-hand rules comes from a calculus thing called the cross product that you'll definitely learn about in college. So we have a different right-hand rule that we can use to determine the direction of the force that acts on a moving charge. All right, and this is the only other right-hand rule that we have. All right, so here's how this right-hand rule works. We point our hand in the direction of the existing magnetic field. So if we're doing the Earth, right, we point our hand north. Then we point our thumb in the direction that our charge is moving, right? So if it's moving up, we point our thumb up. If it's moving down, we point our thumb down. And then our palm points in the direction that that charge will get forced. All right, that's it. Well, that's it if we have a positive charge. If we have a negative charge, then it just is the exact opposite direction. Then the positive charge would get forced. So let's do a few examples together to see how that second right-hand rule works, and then I'll give you a minute to do some other examples in your forcings. So for our first example, what does B stand for? That's the direction of the magnetic field, right? So this first column tells us which way the existing magnetic field points. The second column tells us the direction of the velocity of our charge, and then we're supposed to say what direction that charge will be forced. All right, so for the first one, the magnetic field points down, so I point my hand down towards the floor. The charge is moving to the right, so I'll point my thumb to the right, and then my palm points towards the front of the room. So that will be the direction that that charge gets forced. Boom, done. Questions about that?
Wait.
So you're using your left hand, you gotta use your right hand.
Okay.
Right, this only works with your right hand. Your left hand will be exactly opposite.
That makes sense.
Where is the church?
Charge is moving to the right. Okay, so your hand points down, your thumb points to the right, my palm points towards the front of the room. Other questions about that? All right, next one. Magnetic field points towards the right of the room. I'm going to call the right of the room that way. The charge is moving up, so my thumb points up. What's the direction of the force on it? Towards the front of the room again, so exactly the same as the first example. Brian?
Is this only in relation to like the Earth's magnetic fields?
No. This actually doesn't necessarily involve the Earth's magnetic field. The net existing magnetic field is in these directions, right? So we'd have to have, so for this one where the magnetic field points down, either we have to go up towards the Arctic to get the Earth's magnetic field to point down. Is that true? Yes. Or we need a stronger magnetic field that kind of makes the Earth's not so significant.
But then, I'll come back to it.
All right. Other issues with the use of the right-hand rule for these two. All right, we'll do one more together, and then I'll let you do the rest on your own. Now, for these next few, we're doing east, north, right? We're not doing right, down, left. I'm going to pretend that I'm looking at a map for these ones. If you want to use the real directions because you know which way north is and which way east is, fine. But guess what? You're taking your midterm in the media center, so unless you know which way north is down there also, don't do that. Right? So I'm using a piece of paper and I'm pretending I'm looking at a map. So east is the direction of the magnetic field. I'm going to point my hand towards the right of my piece of paper. So on almost every map I've looked at, right is east. And then the charge is moving north. North is towards the top of the piece of paper. So I point my thumb towards the top of the piece of paper. I'm going to rotate this just for a second so you can see how my hand is, but I am going to do it with my map flat. And then my palm points down. What direction on a map is like into the plane of the paper? What direction is that? It's just down, right? It's just down.
Into the earth.
Because south would be towards the bottom of the piece of paper. This is into the piece of paper, so that's down. All right? So this charge will get forced down into the ground. All right, you guys in your foursomes try and do the remaining four.
West.
Magnetic fields have a charge.
Still down.
No,
No.
they're created by charges, but no, I would not say that it has a charge. It's a disturbing
My thumb says it's been that way.
Yeah,
it's still down. Yeah, because it's just confusing it. It's like
Wait. So